Hello, my name is Jared and welcome to the Synthetic Math series. Today we're going to do part 2, division. Now, if you remember from part 1 where I talked about the concepts, synthetic math is basically synthesizing two things. It's taking a basic math platform, but using algebraic rules and putting those together. Now, when it comes to synthetic division, it's actually based off of Homer's method, which is a method of evaluating polynomials. But we're going to start with using the basic math platform because there's a couple of important concepts that are important to translate from the normal division platform into what we know of as synthetic division. So to do synthetic math, we're going to use this example of 6x to the fourth plus x cubed minus x squared plus 5x minus 6. And we're going to divide it by 2x squared minus x plus 1. But instead of doing it long division where you show all the variables and exponents, we're just going to use the coefficients. So we're going to take 6, 1, -1, 5, and -6. We're going to divide it by, and we take the coefficients of the divisor of our 2x squared minus x plus 1. So we take the 2, the -1, and the 1. It works just like long division. We're using the basic math platform, but we're not writing all the variables and exponents. So 2 goes into 6 3 times. We're 3 digits deep here, so we need to go 3 digits into the dividend. So 2 goes into 6 3 times. Then you multiply it back. 3 times 2 is 6. 3 times -1, 3 times 1. You subtract these, you get 0, you get 4, and you get -4. Then you bring down the next column, 5, and you repeat the process. 2 goes into 4 twice, multiply it back, 4, -2, 2, subtract 0, -2, 3, bring down the next one, -6. 2 goes into -2 and -1 times. So we get -2, +1, -1. We subtract again, we get 2 and -5. So I basically followed the long division way, just without the variables and exponents. This is kind of like quasi-synthetic division. We use the basic math platform. We use algebraic rules in the sense that we're allowed negative values, we're allowed double-digit values. Now, how to translate this back into algebra? The quotient is up here, so that becomes 3x squared plus 2x minus 1. And our remainder is down here, 2x minus 5. So in the quotient, we have our constant column, our linear, and our quadratic. In the remainder, we start with the constant, and then here's the linear. So in this method that we're used to in basic math, there are certain concepts that are really important to bring with us when we get to what we all think of as synthetic division. First of all, place value is important. In basic math, you go by digits. In algebra, you go by terms. But now, because we're using algebraic rules, again, you're allowed negative digits, double digits, or multiple digits in one place value, whereas in basic math, you're not. 0 placeholder. In basic math, you have 0 as a placeholder. In algebra, you do not. Since we're using the basic math platform, we need the 0 as a placeholder if you are missing a power of x. So here we have all the powers of x listed, but if, say, you didn't have an x cubed, you would need to hold that with a 0. Unlike algebra, where we just don't write the term. Then when you get into the actual process itself, here are 3 important things that we want to transfer over. One is that division by the lead coefficient. Notice you divide by the lead coefficient. 2 divides into 6 3 times. That occurs first. Second, the multiplying of your quotient to your divisor. that occurs second. Third, the subtraction here to find the remainder, or what's remaining left here in our dividend. That is what occurs third. Now what's going to happen in synthetic division is this negative is going to get reallocated to the divisor, and we're going to add our columns. So let me set that up and we'll see what it looks like. So real synthetic division, which was based off of Homer's method, I'll put that up here instead of the basic math method, based off of Homer's, that we still use the coefficients. So we'll put 6, 1, -1, 5, and -6. But instead of putting the division on the top, we're going to work downwards. So on the divisor, we bring this down one at a time. We want one divisor component for one row, and we're going to reallocate that subtraction sign to the divisor component. So this becomes a -1, and we leave a row here for that. We bring down the next component, which is a -1. We need to, again, reallocate the negative to that, or that subtraction sign. So this becomes a +1, and it gets a row to itself. And this is where we draw our line here. And this 2, which happens first, the lead coefficient, will come down here at the bottom. So this last row is actually going to be the quotient. Our quotient. That is our answer to the division problem. One thing that we need to establish before we start is where is the remainder at? So in the basic math, the quotient was at top and the remainder is at the bottom. Since everything is at the bottom in this method, we need to separate the quotient from the remainder. So just take your highest exponent, x to the 4th, in the dividend, and divide it by your highest exponent term in the divisor. So x to the 4th divided by x squared is x squared. So that means this column in the quotient will be x squared. This column will be x. This column will be the constant. So your remainder starts right here and goes that way. So quotient, remainder. So what we do here is we bring down our first number, the coefficient of our first term, 6. And remember, the first step is to divide by the lead coefficient. So 6 divided by 2 is 3. You just write it right underneath of that. If your lead coefficient is 1, you're technically still dividing by 1, but it doesn't change the number. So you can get away with 1 row. But since our lead coefficient is 2, we divide by 2, we get 3. Now the second step is to multiply the quotient by the divisor. So 3 times -1 is a -3. Now where do we put that? We're 3 terms deep into the divisor, so we need to go 3 terms deep into the dividend. So 3 times -1 is -3, it goes over here. 3 times 1 is 3, that's 2 terms deep. So we go 2 terms over, keep it in the right row. This is a 3. Once you reach this line, you can now add. Remember, we reallocated the subtraction sign to the divisor components. Notice the negative was not reallocated to the lead coefficient because you're dividing by the lead coefficient happens before the subtraction does. So it only occurs on the other components of the divisor. So since we reallocated that subtraction sign, it now becomes addition. So 3 plus 1 is 4. We again divide by the lead coefficient. We get 2. 2 times -1 is -2. You just continue your columns to the right. 2 times 1 is 2. You now add these up and you get a -2. -2 divided by 2 is now -1. -1 times -1 is +1. Notice we're at the end of our columns here. -1 times 1 is -1. Now, once you reach this point, we now notice we've reached the line again. We've reached the bottom. We add these up. Here we get our 3. And here we get our -5. You do not divide by the lead coefficient into your remainder. So remember, your remainder is written as a fraction over the divisor. So you don't keep dividing it. It's at the end of the division process. So here again, you can translate this back into algebra. 3x squared plus 2x minus 1 with a remainder of 3x minus 5. So the purpose of this video is just to illustrate to you, you can actually use basic math as your platform for synthetic division. It's not quite as efficient as this one. This one is more efficient. You get really fast at this. One of the things that you need to be able to do if you're, say, a teacher or someone who you want to demonstrate it to someone else is if you are generating your own dividend, then you need to create it using the unconventional way of multiplication. What I mean is, if I get rid of this part here, say we take 37 times 12. 37 times 12. The normal way you do math, 2 times 7, 14, 6, 1, 7, and you get 7, and 3, you get 4, 14, you get 444, okay? You can't use 4x squared plus 4x plus 4 and divide it by 3x plus 7. You're not going to get 1x plus 2. What you need to do if you're generating your own examples is to use the unconventional. Remember, basic math platform with the algebraic rules. So if we use this with algebraic rules, it becomes 14, 6, 7, and 3 becomes 3, 13, and 14. It's actually the same thing. 300 plus 13 tens is 130. That's 430. Plus 14 ones is still 344. But this form is the form that you're going to want to use if you're trying to generate algebraic examples, is by using this unconventional way. Remember, you're using algebraic rules. You're allowed double digits per place value. So this would be 3x squared. If we wrote that down, we would now have 3x squared plus 13x plus 14. And we want to divide it by, say, our 3x plus 7 to get x plus 2, the 12, okay? So 3x plus 7, bring this one up here. So we're going to divide it by 3x plus 7. So notice again, use your coefficients, 3, 13, 14, draw your line, bring down your first term, change the sign. We're reallocating the subtraction, so we make it -7. Bring down your lead coefficient, make it divide by 3. So here we bring down our first terms of 3. We divide it by 3, we get 1. 1 times -7 is -7. Notice it's 2 terms deep, so we go 2 terms into our dividend. 13 minus 7 is 6. Divided by 3 is 2. I didn't draw my remainder. X squared divided by x is x. Here's your linear. Here's your constant. This is your remainder. 2 times -7 is -14. There's your remainder of 0. Again, you don't divide the remainder. Here is your x plus 2, or your 37 times 12 is 3, 13, 14, 300 plus 130 plus 14. So you can generate your own algebraic examples where you just replace your x with like a base 10, but you need to generate it using algebraic rules, not your basic math rules. So that's synthetic division. You can do it with polynomials. You can do it with quadratics, cubics. You can do it with lead coefficients greater than 1. You can even do it with complex numbers. It gets a little tedious. But you can, anything that you can divide long division, you can divide with synthetic division. I hope this helps, and see me again in part 3, where what is exciting for me is synthetic square roots, because I have an application for you that you might find exciting. So thanks for listening. Catch you in the next video.